We're on Unit 1 of AP Chemistry, Atomic Structure and Properties. This video focuses on Section 1.3, Elemental Composition of Pure Substances. Buckle up because this is a long one, guys. We're going to go through 8 different examples. The majority of this is working through example problems. None of these are particularly difficult. They just can be a little intimidating when you look at them and think, oh my goodness, what am I supposed to do? Where do I start? Right? So definitely make sure that you practice these and are comfortable with these. All of these are very realistic to what you would expect to see on your Unit 1 test from me if you're in my class, and these are realistic for the exam as well. So the first thing I want to go through with you, a pure substance, if you don't recall, is going to be an element or a compound. A compound consists of 2 or more elements that are chemically bonded to one another, right? Such as H2O, water. Notice those aren't written together, they're bonded. A mixture involves a combination of 2 or more different compounds. So for example, sodium chloride and water, right? That would be a mixture of 2 or more different compounds. So one of the things you'll be expected to do regularly is calculate a percent of some sort. In this case, we're talking about a percent by mass. So when we're referring to mass, we're referring to grams, right? So as all percentages, they're pretty simple, right? A percentage is always the part divided by the whole. And then to calculate it as a percentage, you need to multiply by 100. So if I ask you to calculate the percentage of hydrogen in H2O, for example, as you see here, right, because there are 2 hydrogens in H2O, you're going to multiply 2 by the atomic mass of hydrogen, which you get from the periodic table is rounded to 1.01. And you're going to divide that by the total molar mass of H2O, the entire compound. So again, the hydrogen part divided by the whole mass of the compound. So if we were to add together the 2 hydrogens plus the 1 oxygen mass from the periodic table, that total would be 18.02. So that's where that number comes from. Multiply by 100 and we end up with an 11.1%. Now, if we do the same thing for oxygen, right? There's only 1 oxygen, so we have the oxygen part would be 16 divided by the total mass of the H2O molecule, which would be 18.02. So we end up with an 88.9% here. So since H2O is composed of only 2 elements, 2 hydrogens, 1 oxygen, right? What percentage should we get if we add those 2 together, right? If we're looking for the percent by mass, it should add up to be 100%, or very, very close to 100. Could be a bit off with rounding, but we should be very, very close. And that is example 1. Moving on to a little bit more info here, the law of definite proportions. So the law of definite proportions tells us that we have a ratio of masses of elements in any pure sample, right? And those ratios are always going to be the same. For example, H2O is always 2 hydrogens, 1 oxygen, always, right? So that lets us know that these things are always in proportion to one another. Now, an empirical formula, all right, moving forward, this is how we're going to apply that law of definite proportions. An empirical formula is the lowest whole number ratio of atoms. This is the reduced or simplified form, right? So if we have divided everything, right, by the greatest common factor and gotten down to the simplest form, that would be the empirical formula. Now, a molecular formula is going to be the higher unreduced, unsimplified form, right? They're going to be higher numbers. For example, right, we can have a compound that contains only carbon, hydrogen, and oxygen, but in different numbers, still in ratio to one another, remember, because that law of definite proportions. So a molecular, right, formula, for example, could be C6H12O6. We should recognize that one from biology, right? That's glucose. If we were to simplify that, what would our greatest common factor be, right, of 6, 12, and 6? Right, 6 would be our greatest common factor, so divide all of those by 6. Our reduced form would be CH2O, right, and that would be the empirical formula. This is something you need to know. You need to be very, very comfortable with those definitions in writing, right, as well as in calculation. So that's something we need to be able to do. Now, that being said, how would we play with that? How could we make these problems a little more difficult? Well, first things first, the mass, right, of the molecular, which is the higher number, right, higher valued, unsimplified form, we would obtain by multiplying the number of each atom, right, by its mass. So for example, we have 6 carbons, so we're going to take 6, multiply it by carbon's mass of 12.01. We do the same thing for hydrogen, same thing for oxygen, and we get a total of about 180 grams per mole. Right, we do that for the empirical formula, we're going to see a much smaller value, right, because we have reduced numbers, 1 carbon, 2 hydrogens, 1 oxygen. So if we do that same process, we're going to get a total of 30 grams per mole. Right, so what ratio are we looking at if we compare 180 to 30? Should be a 1 to 6 ratio, right? So the difference in those should be 6 times greater, because our greatest common factor was 6, right, when we were working that. So that's how our law of definite proportions comes into play here. Now, how can we make this math, right, much more difficult? How can we manipulate this and use it to solve all these different types of problems? All right, there are 8 examples we're going to go through. We've only made it through example 1, so get ready. Next part, you're going to be asked to calculate the empirical formula, right? Typically from a percentage, and it's going to be by mass. What does mass mean again? Grams. It means we're dealing with grams. You're using this in pretty much every example problem here. It's just manipulated in different forms. This you need to memorize, right? Big star. Memorize this. Step 1. Right, it's a bit of a rhyme here. Percent to mass. Step 2, mass to moles. Step 3, divide by the lowest. Step 4, multiply. That's what the X means there. Multiply till whole. So percent to mass, mass to moles, divide by the lowest, multiply till whole. If you can turn that into a bit of a jingle, might be a little bit easier for you to remember. But we definitely need to be able to flow through those 4 steps. All right, in example 2, you're going to find an empirical formula for a substance that is 84.2% carbon, and the remaining is hydrogen. Okay, so we only have carbon and hydrogen. Well, how do I know what percent the hydrogen is? Well, if it's only made of carbon and hydrogen, then I know that the entire compound has to be 100% C and H together. So if I take 100, subtract the 84.2%, then I know that hydrogen's percent must be 15.8, right? So 100% minus the 84.2% equals the 15.8. That's where I got that from. Now, we've got to have that percentage of each different element first in order to go through those 4 steps we just discussed for finding an empirical formula, right? These 4 here, we've got to have that information first. So now we've got our 2 percentages, now we're ready to rock and roll. So we're going to start with carbon, go through the 4 steps. Start with hydrogen, go through the 4 steps, right? All right, so carbon. We are going to start with percent to mass. Well, how do you do that? Well, here's the thing. Remember how I told you that if it consists of 2 things, or 3 or more, however many, the sum of those things must add up to be 100%. So in these problems, we can assume 100 gram sample, which makes our math so much easier. So there's no actual calculation you do to change the percent to grams. You just take away the percent sign and write it as grams. So rather than 84.2%, I'm going to write 84.2 grams. I'm going to do the same for hydrogen here. Instead of 15.8%, I'm just going to write it as a G in its place, right, for grams. Now, step 2 on both of these problems, I want to change mass to moles. So starting with carbon, how do I change grams to moles? Well, that conversion comes from our periodic table, right? So remember, our molar mass is how many grams are in 1 mole of that substance. So we're going to take our 84.2, right, and we're going to multiply by our ratio of 1 mole of carbon is to 12.01 grams of carbon. So 84.2 divided by 12.01 gives us 7.011 moles of carbon. See that here. Okay, let's do the same for hydrogen. We got 15.8. We're going to multiply that by 1.01 grams from the periodic table. We end up with 15.958 moles of hydrogen. Now, it's ideal here to keep some sig figs there. I'm not going to harp on sig figs, me personally, for our test over Unit 1. I will for the rest of the year, but because we haven't had enough time to review sig figs together, that'll start coming into play more into Unit 2. But it is just more helpful to you if you can keep some sig figs here. All right, so we've done step 1, we've done step 2, we're on to step 3. How do we do that? Compare these 2 numbers of moles, right? Which one's smaller? We got 7, we've got 15. Obviously 7's smaller. So you want to divide both of these, both of them, very important, by the lowest number. So 7.011 divided by 7.01 gives us 1. 15.958 divided by 7.011 gives us 2.276. Well, that's not a whole number. Okay, so here's the problem. Step 3 is complete, but step 4 tells us we're going to multiply into a whole. Well, how do we know what to multiply by? Well, we need this to be a whole number, so we're going to give it our best guess. We're not concerned about the 1, it's already a whole number. Whatever factor we choose to multiply it by is still going to be a whole number. So we're going to start with our decimal number. That's what we need to correct, 2.276. If we multiply it by 2, we're still getting a decimal. If we multiply it by 3, we're still getting a decimal. You can try this in your calculator. We're not really close to a whole number. And what do I mean by close? I mean within a tenth, right? So I like something, say 8.94, 8.98 would be better. 8.01, those are acceptable numbers that we could round to, right? So within 0.1 of a number, for me, I want to be at least there. So I see when I put in my calculator that 4 works. That gets us very, very close to 9. So that leaves us with 4 for the carbons and 9 for the hydrogens. Well, what does that tell us? That tells us our empirical formula. That tells us exactly how many carbons we have and how many hydrogens we have. So it leaves us with a formula of C4H9. So the problem here is that our original problem asked us for a molecular formula. It did not ask us for an empirical formula. So how do we do that? How do you find a molecular formula? Okay, so to find, I might need to add this in because I don't think this was in my original PDF of the lecture notes. To find a molecular formula, if we have the empirical formula, okay? All right, you want to divide, right, the molecular mass by the empirical mass. And that will give you the factor that we need to multiply the empirical formula by. That gives us our final answer. So how did we do that? Well, it told us up here, right, in our original problem, that the mass of the molecular formula is 114 grams per mole. Well, if I find the molar mass of the C4H9, right, it comes out to be just about half of 114, right, just about half. So what that tells me when I divide those numbers, right, that I need to multiply these numbers by 2 in order to get our molecular formula. So therefore, I'm going to multiply C4H9 by 2, so I get C8H18, which is what you see here, and that's how I determined that. Now, how did I know it was half? Well, let's work it out. 12.01 times 4. I can mentally do this math and get an estimate to know it's going to be about double. It has to be by a whole number factor, right? Every time this will give you a whole number factor. So 12.01 times 4 should give me 48.04. And then I have 1.01 for our hydrogen, right? Times 9, which gives me 9.09. Right, so 48 plus 9, right? And we go from there. So that's going to give us 57.12, which is about half of 114, right? So that's how we solve that mathematically. So we'll take 114, divide by 57.12, and go from there. All right, moving on. Example 3. The same, but different. We're going to go through a lot of the same steps as we move forward, but this one's presented differently, all right? So we got a pure sample of gold with a mass of 41.95 grams, and it's burned in air until all of the gold is consumed to form gold oxide with a mass of 47.07 grams. Determine the empirical formula. Okay, we talked about that. That's our 4 steps thing, right, of the gold oxide compound. So this one's a little tricky because it expects you to know a little chemistry here. You've got to know the reaction. So I know I've got gold. This wasn't given other than in words in the problem. I figured this out. When it says burned in air, that is always going to mean I'm adding it to oxygen. Oxygen is what we're concerned about it burning in the air, right? And it tells us that we're going to form something called gold oxide. Okay. So since we know that, and we know that the gold oxide is going to have a mass of 47.07 grams. I wrote that underneath for simplification. And I know that the gold had a mass of 41.95, right? So I wrote that here. What I don't know is the mass of the oxygen. Don't know, but I can figure it out because there's this thing called the law of the conservation of matter, right? So mass is going to be conserved. So what that tells us is the sum of the reactant masses, these are reactants on the left side of the arrow. Just as a reminder, your products are on the right side. So the sum of these two things must equal that. So if I know that that's the final answer, I can simply take our 47.07, subtract the 41.95 grams, as I've done right here, and that tells me we have 5.12 grams of oxygen, right? And in these problems, it's a little different. Normally, we would assume that oxygen, right, would be O2. Typically, oxygen's a diatomic element. We always assume it's O2. But when we're dealing with empirical and molecular formulas, we always go with the simplest elemental form with a single, right, atom of each element, regardless of whether it's diatomic or not, typically, right? Because we're trying to find that molecular and empirical formula. If you don't recall this from math, this little 3 dot sign is something we're going to use a lot. It represents the word therefore, and we'll use that pretty often. So now that we have our grams of oxygen, now we have the information we need to do the 4 steps, right? We've got to have that. So this problem is a little different. We're actually going to deal with 3 steps instead of 2. Why? Well, we don't have a percent. We do, but we don't. So instead of a percent, this one's a little easier. It's already turned it into grams for us. We already know what the grams are. If we already know the grams, well, then we don't need to deal with the percentage that's already taken care of for us. All right. So I want you to start with your 41.95 grams of gold. Right? We're going to divide by the molar mass of gold from the periodic table here, the 196.97. I'm going to get 0.213 moles of gold for an answer. Do the same for oxygen. I'm going to take our 5.12 that we found through subtraction. I'm going to divide by 16 grams of oxygen, which I get from the periodic table. And I'm going to get 0.320 moles of oxygen. Now, that's step 2. Back to our 4 steps again, just as a reminder, right? Step 1 complete, because we didn't have to do that. Step 2 is done. Step 3 says divide by the lowest. So let's compare these 2 numbers of moles. 0.213, 0.320. Which one is the lowest? 0.213. So we're going to divide both mole numbers by 0.213, simply because it's the lowest. When I do that here, divided by itself, obviously, I'm going to get a 1. When I divide here, I get 1.5. Now, if we got whole numbers for both of these, we could stop at this point, but we did not. We got 1.5. We're not even close to a whole number. So we're going to have to multiply both of these by a factor, which is what step 4 tells us to do, until we arrive at a whole number. Well, 1.5 is a pretty easy number to work with. I know that if I multiply 1.5 by 2, I'm going to get 3, which is a complete whole number. So if I multiply both of these by 2, I have whole numbers of 2 and 3. Therefore, my empirical formula for the gold oxide is Au, gold 2, oxygen 3, O3. All right, so we're able to figure out our empirical formula. All right, not so bad, right? 4 steps, just presented a little differently. Let's move on to example 4. Now, example 4 is something pulled from Michael Faribault's notes. So many of these problems I have created myself, but I tried to note the ones who came from Michael Faribault. Just give credit where credit is due. So for this particular one, he told us that we have something called compound X, and it consists of carbon, hydrogen, and nitrogen, right? 3 things. And there's a 15-gram sample of this compound X. And we know that 9.81 grams of it are carbon, 1.37 grams of it are hydrogen, and 3.82 grams of it are nitrogen. And we are tasked with finding the empirical formula. So we're going through our 4 steps, right? So the first one tells us percent to mass. Okay, we don't have any percentages. Guess what that means? Well, in this case, we don't have to worry about finding a percentage. Yay for us. So since we know that this is the complete sample. So step 1's already done for us. Step 2, we're going to change mass to moles. So we want to change grams to moles for each element individually. So start with carbon, right? We're taking our 9.81 grams of carbon, dividing by 12.01 grams, which is from the periodic table. We get 0.817 moles. Repeat it for hydrogen, 1.37 grams, given in the problem, divided by 1.01. It's our molar mass from the periodic table for hydrogen. Remember, only use one of everything, right? When we're finding empirical formulas, we don't care that things are normally diatomic. All right, we get a 1.36 moles of hydrogen. Again, for nitrogen, right, with our 14.01 from the periodic table, we get a 0.273 moles of nitrogen. Those numbers is the smallest. 0.8, 1.3, or 0.2, obviously the 0.2. So moving on, step 2 is complete. Step 3 tells us to divide by the smallest. So take all 3 mole numbers, divide them all by the smallest mole number we have. So divide them all by 0.273. Bam, bam, bam. Obviously the number by itself gives us 1, divided by itself gives us 1. 1.36 divided by 0.273 gives us 5 for that one, and this one gives us 3. Fantastic. These all worked out to be whole numbers. What about step 4? Well, step 4 says multiply by a factor until whole. These are already whole, which means step 4 is irrelevant for us. It's unnecessary, so we're not going to use step 4 for this problem. If we had gotten a decimal, if one of these was 2.29, 3.78, we would absolutely have to use step 4 and continue multiplying by factors till we got whole numbers. Since we have whole numbers, right, we're done with finding the empirical formula here. Yay for us. So we have 3 carbons, 5 hydrogens, and 1 nitrogen, C3H5N. So that is example 4, part A. Moving on to part B. We've got a 25-gram sample of this compound X. It has 9.11 times 10 to the 22nd molecules. We're told to find the molar mass of compound X. So molar mass, just a reminder, is always in units of grams per mole, which are 2 units. So I know that however I set this problem up, I need my answer to have 2 units at the end, and I need them to not cancel out, right, when I set up these dimensional analysis problems, which are where we're multiplying by something over something each time, right? So I know that that needs to guide our thinking and how we set the problem up. I'm given grams in the problem, and I'm given molecules, right? So my thinking is, well, I know I need grams in the answer, so I don't want to mess with that. I don't want to use the 25 grams because I need grams as part of the answer because I need it to be grams per mole. I don't need molecules. Molecules and moles are not the same thing, right? Molecules sometimes are also referred to as particles or atoms when we're dealing with Avogadro's number, right? Those are the terms we use that tell us, hey, we need to use Avogadro's number. So this is one of those situations. So I'm going to start with the molecules, right? The 9.11 times 10 to the 22 right here. And I'm going to convert that into moles. Right, so I'm going to divide by Avogadro's number here, 6.02 times 10 to the 23rd, and I get 0.15133 moles of this compound X. All right, so now I have moles, and I had a number with grams already, right? So if I take that number that was given in grams and divide it by the moles I just found, I now have an answer, right, in grams per mole. So 25 divided by 0.15133, and I get 165 grams per mole. And that is how we would calculate that molar mass. Not hard, but it looks a little intimidating, right? So that extra step of trying to figure out where to start. So don't overthink it. Focus on what's given. Don't let the words trip you up. Focus on what units you're given and what units you need to find. All right, still on example 4, but we're moving on to part C. Based on your answers to parts A and B, find the molecular formula of compound X. Okay, so this tells us we need to use A and B. One good thing about the AP exam is they tell us we need to use A and B, we need to use parts A and B. So our empirical formula is C3H5N. How do I know that? Well, because that was the answer for A, right? So I'm going to figure out what the formula mass of our empirical formula was, right? What's the empirical formula mass? So I'm going to take 12.01, that's our mass from carbon from the periodic table, times 3 carbons. Doing it again for hydrogen, right? 1.01, there's 5 of those, so multiply by 5. And nitrogen, we only have 1 of those. So we're going to add the 14.01 to the total of the others. Be careful with this in your calculator. Use your parentheses, set that up correctly, or you're going to get a number that doesn't make sense, right? So we always want to check with something that makes sense. It's a good rule of thumb here. So we get 55.08, right? I know that's reasonable because I can look at, okay, 12 times 3 should be 36. That's about 40. 1 times 5 is 5, so 45 plus 14, which I like to say 15. So that should be about 60, close somewhere in the ballpark, right? If you get a number like 2,512, we know that doesn't make sense. Okay, from there. So remember to find a molecular formula, right, or a molecular mass. We use those, the molar masses, right, of each one of those, of the empirical formula and the molar mass of the molecular formula. Those are the two things we use in order to determine our molecular formula. So we got to have that empirical formula first, which we do. So what we're going to do is we're going to divide our molecular molar mass, right? These have to be given to you from a real sample. You can't just know that. You've got to have some information. So your key for this is it's given to you in the problem as a real sample, right? The empirical formula mass is not going to be. That's something you're going to have to calculate. And usually you've already done that in a previous step. So what we're going to do, right, is take our 165 grams per mole and divide it by the 55.08 grams per mole that we just found. When we divide those two numbers, we get an answer of 3. What does that tell us? That tells us that that's the factor that we need to multiply, right, the empirical formula by. So I need to take our C3H5N, right, you see right here, and multiply each number by 3 to find out our molecular formula. So that's how I end up with the C9H15N3. Final answer. That is our molecular formula. Check. Done. Moving on from example 4. Moving on with example 5. So a little background from example 5. Combustion. Combustion is one of the 5 main reaction types, and you are expected to know what a combustion reaction is. So combustion is usually defined by a hydrocarbon, which is some combination of C and H, right? A hydrocarbon means simply carbon and hydrogen put together in some ratio. And that reacts with O2 to form specifically CO2 plus H2O. So you should know that this is what a combustion reaction looks like. It only forms carbon dioxide and water. So these are pretty easy. This you need to be able to memorize. You need to know that this is combustion. So this is another Michael Faribault example from his notes on Unit 1. So we're told that we have a sample of a compound that contains carbon, hydrogen, and oxygen. It's burned completely in oxygen, and we're given data from this experiment in a table. Right? So here's our table we're working with. So we know that we have 5 grams of the sample that's burned. We know that the mass of the carbon dioxide produced is 10.99 grams. We know that the mass of the water produced is 6 grams. So we want to know the carbon in the 5 gram sample, but here's the issue. We can't use the 5 grams in our math because we don't know the chemical formula of the hydrocarbon in the compound, so we don't know how many carbons are in this compound that's being burned. So what we've got to do is look at our table and work with the only option that contains the thing we're looking for, which is carbon. So we can't use this one, right? Not a choice. So we've got H2O and we've got CO2. Well, we're trying to find carbon, so H2O is not going to be helpful to us. So we want to use the compound that contains carbon, so CO2. So let's start there. We're going to start with our 10.99 grams of CO2 given in the table. So let's think. I need to figure out how to get carbon out of CO2. So I have grams of carbon dioxide. So I need some sort of ratio, right? That is carbon to carbon dioxide. And since we're dealing with grams of CO2, I need this thing on the bottom to also be grams of CO2 so that they can cancel. So where can I get a number of grams of CO2 that's not the given number? Where can I come up with that? Well, I can do the molar mass. Yeah? So where do I get molar mass from? The periodic table, right? So stay with me here. So I have CO2. So I have 2 oxygens times a molar mass of 16, which gives me 32. Carbon, I've only got one of those, so it's 12.01 from the periodic table, right? We're not multiplying by anything, so there's only one. I'm going to add those together. When I do that, I get 44.01, right? That's our grams of CO2. So I can set up a ratio of carbon to carbon dioxide. Our grams of carbon, right, is simply 12.01. from the periodic table. So now I have carbon to carbon dioxide. And this works because what I want to do is convert the grams of carbon dioxide to grams of carbon. So grams of carbon dioxide cancels. So I'm going to take my 10.99 in the calculator, multiply it by 12.01, and then divide it by 44.01. Right? When I do that, I hit enter in my calculator, I get 2.999 grams of carbon. And that solves part A. Part B. We are told to determine the mass of hydrogen present in the 5-gram sample. The exact same thing we just did, but we're dealing with hydrogen this time. Well, here's the thing, just like before, it didn't tell us the carbon in the chart. It doesn't tell us the hydrogen in the chart. So what we want to do is choose the next best thing, right? The option that contains hydrogen. So this time we want to use H2O to solve our problems. Now, a given number of H2O is 6.00 grams. So we're going to start this problem with 6.00 grams of H2O. We're going to set up a ratio of masses just like before, right? This one's slightly different though, so I want you to notice something, right? Notice that on our periodic table, right, we're going to find the molar mass of H2O just like we did before. HO, we got 2 hydrogens, so 1.01 times 2 gives me 2.02. Oxygen, there's only one of those guys, so 16. 16 plus 2.02 gives us 18.02. So that's where this number comes from. Notice the top. Why is it 2.02 for hydrogen instead of 1.01? The periodic table says 1.01. Well, I want to know the ratio of hydrogen, right, in the sample of H2O. So that contains 2 hydrogens, so that makes a difference. Be careful. We didn't have that before because when we were dealing with CO2, right, in the previous problem, there's only 1 carbon in CO2, right? So that was simply 12.01 for the carbon. But because we have 2 hydrogens, we got to multiply it by 2, so we get that 2.02. Now, mathematically, solving it the same way, make sure we get this. It's a trick, it's a trick. Right, so mathematically in the calculator, you're going to type in 6 times 2.02, and then we're going to divide that answer by 18.02 to get our final answer of 0.671 grams of hydrogen. All right, moving on to part C, we're told to determine the mass of oxygen in the 5-gram sample. Okay, a couple of different ways we could do this. We could go back and do the same process we did on part A and B. Except we would start with either carbon dioxide or water because both of those would contain oxygen, which is what we're searching for. You could pick either one, go through the same process and solve it. Or because we know this thing only contains carbon, hydrogen, and oxygen here, and we already know what these 2 things are, we know that all 3 of them, carbon, hydrogen, and oxygen, have to add up to equal 5 grams. So because we know the total is 5, and we already have 2 of the 3 parts that make up the 5, we can just subtract and get the difference to find oxygen. Feel free to do it the other way if you'd like, but I tend to lean towards the most direct way. So 5 grams minus our 2.999 grams of carbon that we found in part A, minus the answer from part B, 0.671 grams of hydrogen, leaves us with 1.33 grams of oxygen. Done with part C. Part D, we're told to find the empirical formula now. Okay, that's our 4-step thing, right? So I want to remind you, right? It's percent to mass, right? Grams or mass, and then we're going to do mass to moles, divide by smallest, and then multiply till whole. Right. So lucky us, parts A, B, and C, we already found the grams of all these things. So we're skipping step 1 because we don't have percentages. We already have grams. Right, so we're going to take each of those grams we found and we're going to change them to moles. Okay. So our 2.999 grams of carbon, we're going to divide that by 12.01 from the periodic table. We're going to do the same for hydrogen, divide by 1.01 from the periodic table. Okay. And for our oxygen, we're dividing by 16 from the periodic table. And remember, when we're dealing with empirical formula, you always use 1 for each thing. We don't care if it's diatomic. We're not concerned with the ratios that we were using before, right? That was a different thing. That's when we were dealing with essentially a percent, a part of the whole. Here we want to find out what each individual element makes up for the empirical formula. So once we do all those divisions, we're going to get our number of moles, right? So this would be the end of step 2. We converted to moles. From there, we're going to divide by the smallest. Which of these mole options is the smallest? 0.08, 0.6, or 0.2? 0.08 is going to be the smallest. Divided by itself obviously gives us a 1, right? When you divide 0.666 divided by it, we get an 8. 0.2497 divided by it, we get a 3. So don't need to do step 4 here because these are already whole numbers, so there's no need to go any further. So therefore, our empirical formula has 3 carbons, 8 hydrogens, and 1 oxygen. 6. This time we're going to be talking about hydrates. In problem 5, we were talking about a particular reaction called a combustion reaction. This time, we're going to be talking about hydrates, which aren't a particular reaction type. Hydrates are something that is attached to any compound, generally ionic compounds. So what do they look like, right? A hydrate, right, is a water molecule, and they are included after, always after, any compound by a dot and H2O. Now that doesn't mean multiplication when you see that dot, it just is a separation to show you that water is a part of this compound. It is included on the end of it. Now there can be a number of H2Os there. There can be 2, 5, 10, you know, any value of numbers of H2Os on the end of a hydrate compound. Now, new term, anhydrous. Right? Something that is anhydrous does not contain water. It's not a hydrate. In layman's terms, we refer to that as dry. It means the water has been removed. And how do you think that we remove water? Well, in a lab setting, we'll remove water by heating, right? So we'll evaporate the water away from the sample. So example 6 is a Michael Faribault problem from his Unit 1 notes. So he tells us that we have a sample of copper 2 sulfate pentahydrate representing 5 water molecules, and that this sample has a mass of 25 grams. And we're asked to find the mass of copper sulfate in the 25-gram sample. So we know the total mass of the whole thing, including the water molecules, is 25 grams. We want to know how much of that 25 grams is actually copper sulfate. So again, these aren't tough. Don't let this intimidate you in the beginning. So the first thing we need to do is find the molar mass of copper sulfate because that's what we're looking for. So copper has a mass of 63.55 from the periodic table. We're going to add that to the sulfur and the 4 oxygens, so 4 times 16, and we're going to get a total of 159.61 grams per mole for our copper sulfate. Now we want to know, what is the mass of the copper sulfate if we include the pentahydrate, right? So we're going to take the copper sulfate mass, which we just found, right? That's the CuSO4 parts. We just figured that out. And we're going to add the 5 waters to it. So if we add 5 waters times 18.02, where'd I get 18.02? 2 hydrogens plus the 1 oxygen of 16 adds together to give us 18.02. That's something you'll probably memorize throughout the course because it's something we use so often. So 5 of those water molecules gives us a total of 249.69 grams per mole as the mass of the whole thing, right? So now what we want to do is set that up in ratio just like we did in previous problems. So we're going to take our given value of 25 grams of the whole thing, and we're going to multiply by the molar mass of the copper sulfate over the molar mass of the entire compound, the copper sulfate pentahydrate. Okay, so that is going to allow the grams of copper sulfate pentahydrate to cancel, right, and leave us with grams of copper sulfate. Dun, 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 dun. Final answer for A, we get 15.98. And to clarify, when you type this in your calculator, you're going to type in 25 times 159.61, enter, divided by 249.69, enter, and we'll get 15.98. Moving on to part B, we're told to find the mass of water this time. Okay, same situation again. A couple of different ways we could do this. We could set it up the same way we did before, start with our 25 grams of copper sulfate, but this time put the molar mass of the water on top here, right, divided by the molar mass of the whole thing, which we'd already found, or, since we know that it only has 2 parts, it has copper sulfate and the waters, or the hydrate part. And we know the whole sample is 25 grams, so we could just simply subtract our answer of 15.98 from the 25 to get our total grams of water. I tend to go with the more direct method. Do what you're comfortable with. Same answer either way. All right, example 7. Again, a Michael Faribault problem from his Unit 1 notes. This time you're asked to find the percentage of water by mass in calcium chloride dihydrate. So similar process, we want the molar mass of the calcium chloride, right? So we're going to add our calcium part from the periodic table, 2 times chlorine, and get our total of 110.98 grams per mole. Then we're going to work on our molar mass of the calcium chloride dihydrate. So we're going to take that answer we just got, that's the calcium chloride part, right? And we're going to add the water part to it. We've got 2 waters, and we know that our molar mass of water, again, is 18.02 because, well, oxygen is 16. Hydrogen is 2 times 1.01, which is 2.02. Add that together, you end up with 18.02. That's where we get that value from, you see here. Now, add that together, get a total of 147.012 grams per mole. So to get our percent by mass, I'm just going to follow the same steps that we did before. I'm going to take the water part, right, which is 2 times 18.02, because it asks us to find the percentage of water, and divide it by the total of calcium chloride dihydrate, 147.012. But to make it a percent this time, I'm just going to multiply by 100. It's the only difference from the steps that we did before. I need to multiply by 100 to get us our percentage, and I end up with 24.51% H2O by mass. Moving on, finally our last problem, example 8. Again, this is a Michael Faribault problem from his Unit 1 notes. Okay, so we're given a lot of information in this one. We have this giant data table, and we're told that there's an experiment, and we have a sample of a hydrate of magnesium sulfate with some number of waters attached to it. And we're told that it's heated in order to remove all the water from the sample, as we discussed before with lab procedures. And we're given all this information, right? So we have this container that has the hydrate salt in it initially in the picture, and we see that it is heated to evaporate all the water, and then at the end we have an anhydrous salt. So just to remind you what we said earlier, that means a dry salt, there is no more H2O at the end, right? So H2O is all evaporated and gone. So we're told that we have the mass of the empty container, and then we have the mass of the empty container and the hydrate salt before heating. That's important because the difference in those two things is what tells us how much the actual salt weighs. So that's something to be careful with. Oftentimes AP will give you this where you need to subtract, right, the initial weight of some container in order to determine an answer. All right, so what are we actually asked to do in this problem that tells us all this stuff about some experiment? We're told to explain how the data indicates that all of the water has been removed from the hydrate salt in this experiment. Okay, pictures are helpful, but that's not what they want. They want you to articulate. How do you know? How can you look at this data and explain that all of the water has been removed? So if you look at this, what I want you to notice is the numbers keep decreasing. We've got 28.4, right, down to 26.9 to 26.8 to 26.8 again, right? And if you'll notice, these two are almost the same, right? Very, very close to the same number. 26.853 is the third decimal place out. 26.852, right? Where we're seeing a difference of 1 in the third decimal place out. So that's where I see that the mass of the sample is no longer changing, right? So that tells us, right, and the way to term this is going to be important for you guys, right? So pay attention here. The mass of the sample decreases when the water is removed. Makes sense? And we know that all of the water has been removed from the hydrate salt after the third heating. That's important. How do I know it's the third? Right? Because there is no significant mass change between the second and third heating. So I know after that third heating, I'm good to go. I don't need to continue. However, if there was still a pretty big change in that first decimal place, for example, I'm still seeing a change in the mass, that would mean I would need to continue to a fourth heating to be sure that all of the water has been driven off. You'll hear that term, driven off, which just means in this case, evaporated away. All right, on to part B. You're told to calculate the mass of the hydrate salt used in the experiment. So what does that mean? The hydrate salt is the part that has water in it. So that means it's referring to the beginning of the experiment because the water's still there, right? It can't be in the middle of the experiment because we've gotten rid of some of the water. And at the very end, we don't have a hydrate salt anymore. We now have an anhydrous or dry salt. So we've got to go back to the beginning. So this is where I'd mentioned before, we want to subtract the mass of the container from the mass of the container and the hydrate salt together, and we get the final answer. That easy, and sometimes the questions are that easy on the exam for a part A, for example. Okay, moving on to part C. Now we're told to calculate the mass of the water removed from the hydrate salt. Okay, so we're going to take our hydrate salt, the 28.418, right, that number from the beginning, and we're going to subtract the mass of the dry salt. Where do I get the dry salt from? Well, that's the last number after that third heating, right? So this is the number from after the third heating, because that's when we know the experiment's done. The difference in those tells us how much water we lost, because remember that law of conservation of matter, right? So that mass has to go somewhere. It can't just disappear. So that would tell us that 1.566 grams of water has been removed from the sample. Part D, we're almost there, guys, home stretch. Next, we're told to find the value of N in the magnesium sulfate hydrate, right? So we want to know how many waters is present in this compound. So how can we figure that out? Well, we've already figured out, right, how much our anhydrous or dry sample was. We did that earlier. And we know that N represents a mole ratio, okay, of the moles of H2O to the moles of magnesium sulfate. And we know the mass of the anhydrous salt, and we know the mass of the water. We figured that out, right, in a previous step. So if I can figure out how many moles of magnesium sulfate we have and how many moles of water we have, I can do that thing we did before, like the molecular and empirical formula, and figure out the ratio to find that factor that we talked about, right, to tell me how many waters that we have in this hydrate. So I'm going to go through essentially that four-step process again, right? I'm going to start with our grams of magnesium sulfate, right? And then I'm going to start with our grams of water. Those are the two components that we have, magnesium sulfate, right? And water. Those are the two things that I need grams of in order to do this ratio situation. So I'm going to take the grams of magnesium sulfate and divide by its molar mass, right? And I'm going to get the number of moles here as 0.01243. I'm going to take the grams of water that we figured out earlier, and I'm going to divide it by the mass of water, right? And I'm going to get the moles of water here, right? So now that I have the moles of each thing, I can set that up as a ratio to determine that factor. I don't have to continue to go forward from there. So N would be equal to the moles of water divided by our moles of magnesium sulfate. And when I do that, I get a value of 7. Therefore, right, N is equal to 7. And our formula is magnesium sulfate heptahydrate. Hepta represents 7. And that concludes all of 1.3.